Hello and welcome to this recorded e-learning on the Chipscope Pro software. My name is Srikant and I will be your instructor for this module. In this module, we will learn about the in-circuit verification capabilities of the Chipscope Pro tools. If you are an experienced ASIC designer or new to FPGA design, this module will help you reduce your learning curve and get productive faster with your new FPGA design. This module will help you debug and verify the functionality of your design. The practices covered here promote fast and efficient debugging. The objectives of this module are to get you up to the speed on the basics of using Chipscope Pro software. That includes being able to describe how the Chipscope Pro software works, but also the benefits of using Chipscope. We will describe the Chipscope cores that are available and how to use the Chipscope core code generator and co-inserter tools. It will also be helpful to you if you can plan to use Chipscope early in your design flow. This will enable you to plan for sufficient resources to be available for debugging your design. But first, we are going to discuss the importance of being able to perform on-chip debugging of your hardware design with the Chipscope Pro software. Well, as we all know, FPGA designs are becoming larger and more complex. Designs are running at a higher speed, and designers have less time to design, simulate, and debug their FPGA hardware. In fact, a recent FPGA design survey indicated that debugging and verification accounted for nearly half of the entire design time. As design speeds and size have increased, debugging and verification has become more challenging. To help improve design time, Xilinx recommends the use of its Chipscope Pro software. This enables die-level testing of a design by applying stimulus to internal nodes of a design and retrieving the resulting signals using Chipscope cores built with FPGA resources. To do in-circuit verification with Chipscope, you will apply stimulus to many nodes in the FPGA and store the generated signals using FPGA block RAM and other logic resources. The generated results can then be displayed with a Chipscope Pro logic analyzer. This allows you to quickly verify the operation of many nodes and verify the operation of your device in circuit. Electronic debugging involves probing a design to determine what is happening on the chip at the die level. To do this, the Chipscope cores are placed in the FPGA and can be connected to the nodes the user wants to test. This enables a user to test portions of a design independently. Then verify the design's functionality in an iterative fashion so the user can break the design down into several major components, test the various input and output signals of each component, and finally decide about making any design changes. The design can then be changed, resynthesized, re-implemented before the FPGA is then reprogrammed. This iterative debug process is possible because of the reconfigurable nature of the FPGA. It speeds the entire design verification process and gives the engineer a great deal of confidence that his design is operating properly and reliably. The Chipscope software makes debugging easy since it allows users to test parts of a design and enables a fast iterative process. This can reduce your overall design time by 25% and reduce on-chip verification and debug time by 50%. Since Chipscope uses FPGA resources in its component construction and verifies functionality at the die level, there isn't any external delay inserted into a sample path. This removes the unnecessary timing variation when you debug with oscilloscope or other logic analyzer solutions. Chipscope software is also tightly integrated into the Xilinx FPGA design flow and offers specialized flows that support all of the Xilinx customers. This includes optimized cores for DSP and embedded design. So Chipscope is a powerful tool that is easy to use and tightly integrated with the ISC software. The Chipscope Pro software was originally designed to solve the problem of looking inside an operational FPGA without having to bring collections of signals to I/O, which impacts performance, routing, and requires an external header for connecting to a logic analyzer or scope. Over the years, it has gained in versatility and power and can now be used to inject signals into the FPGA using the VIO core. The Chipscope Pro tool can display sample data in many fashions: waveform, data lists, and data time plots. The data list can be saved to disk and used as inputs into a simulation. Similarly, the same stimulus that drives the simulation can be played into a VIO core to drive the hardware. In this way, the Chipscope Pro tool supports simulation, and it should never be used to replace simulation. The system monitor, which measures the FPGA's temperature, voltages, and other parameters, is accessible via the Chipscope Pro software. This slide shows the debugging cores that may be required for debugging your design. The VIO core, or Virtual Input-Output core, is used to apply stimulus and read output transitions on nodes that you select. You can think of this core as a virtual test header that can be placed on any node in your design. The ILA core, or Integrated Logic Analyzer core, is a capture core. It can be used to create custom triggers that, when activated, cause the storing of data during circuit operation. These conditions are placed by you to control when your system signals will be stored. Your sample signals are then encoded in your FPGA's block RAM for later retrieval via JTAG. The ILA core allows the user to customize the width and trigger ports so that different sizes of data can be retrieved. The ILA core is a basic core used in most HDL designs. The IBA, or Integrated Bus Analyzer core, is optimized embedded designer's core that is used for building designs using Xilinx microblaze soft processor core or a dedicated PowerPC core. The IBA core allows designers to analyze PLB or OPB bus signals and offers protocol detection, which is necessary since embedded designers are often testing their custom peripherals using Chipscope. Chipscope makes it easy to sample the most commonly sampled signals on these buses, such as control, address, and data signals associated with these buses. The Agilent Trace 2 core is commonly called the ATC2 core. This core is useful for storing large amounts of data off-chip or when a customer is using the Agilent Trace Port Analyzer. It offers on-chip debugging of Xilinx FPGAs with the Agilent's FPGA dynamic probing feature. The Chipscope cores use FPGA logic resources in their construction. Block RAMs and slice resources are used for storing trigger conditions and data. The FPGA slice resources can also be used for comparing the internal signals with your trigger conditions. The Chipscope cores will require a significant amount of resources, so you will have to plan on leaving room for them in your FPGA. This sometimes means that users have to use a larger part for testing and prototyping and then use a smaller part in this same package for production. To help with planning sufficient resources for debugging, the Chipscope Pro software has a built-in resource estimator as part of the code generator and core inserter tools. This makes it easier for you to plan your debugging as part of the design construction. There are 3 flows available to add the appropriate Chipscope cores to your design. You can choose between the code generator flow, the core inserter flow, and the plan ahead flow. The plan ahead flow is just like the core inserter flow, but integrated into the plan ahead software. The code generator flow requires you to directly instantiate the codes into your HDL code. This has the advantage of giving you access to all your HDL nodes for testing. Additionally, some of the Chipscope Pro cores can only be added to your design when instantiated into your HDL. For example, the VIO core can only be added with the code generator flow. The disadvantage is that your HDL code will have to be modified to instantiate these cores. Also note that to remove these cores from your design, you would have to comment them out. The core inserter flow is a simpler process that adds the codes directly into your synthesized netlist. This flow is much simpler if you are doing some rudimentary debugging and don't require all of the available cores. Note, however, that the inserter flow only allows codes to be connected to the nodes available after synthesis. So Xilinx recommends that you maintain your design's hierarchy during synthesis. This will assure that most of your primary nodes are available for debugging. Another way to ensure that essential nodes will be available to you for debugging is for you to apply a keep or save synthesis option. Please note the use of this option will depend on your synthesis tool, so check your synthesis tools documentation. Regardless of which flow or synthesis tool you use, the implementation is completed by the Xilinx ISA software. There are no special implementation tools required. After implementation, you can then use the Chipscope Pro software to program your FPGA and debug your design. Finally, note that insertion of Chipscope cores is also supported by the EDK toolkit for embedded design and system generator software for DSP design. The Chipscope Pro software is a complete debug and verification environment that can be used with any FPGA design. To add Chipscope Pro cores, you add them like you would add any HDL component into your design with the ISA software. So use the command project new source. This opens a new source wizard. You name the Chipscope definition and connection file. This will contain all of your Chipscope cores into one source file. Just name the file and then the GUI will open, allowing you to add the cores into your design. Note that the created cores are associated with your top-level design file automatically. But this can be altered. Double-clicking the CDC file automatically starts the Chipscope Pro software. There are two types of Chipscope cores. There are capture cores, which create triggers and store data, and control cores, commonly called icon cores, which interface capture cores to the JTAG chain. The icon core or integrated control core allows you to control and interface the JTAG chain with up to 15 capture cores. There are a number of different capture cores to choose from. The ILA is most frequently used for HDL designs. Each ILA core can be customized for the number and width of signals to be captured or triggered. The ILA core is the most commonly used capture core. The ILA and icon core are supported with the inserter flow. The ATC core is similar to the ILA core except data is captured off-chip by the Agilent Trace Port Analyzer. This is especially useful if you are storing large amounts of test data off-chip. This may be helpful since the available number of block RAMs vary by device and device density. There is a separate hardware product available to Chipscope users. So for more information, check our website. The integrated bus analyzer core has two versions, one for the OPB and another for the PLB bus. These are embedded buses that are frequently used by our customers using our Embedded Developers Kit or EDK. I am targeting either the Microblaze soft processor core or the dedicated PowerPC available in some of our device families. Now these are especially helpful to users that are debugging the behavior of custom peripherals attached to either the PLB or OPB bus. The VIO core, as mentioned earlier, is used to define and generate virtual I/O ports. The ILA cores can be instantiated into your HDL code with either the code generator or added to your design's netlist with the core inserter flow. The ILA supports up to 4 trigger ports with a single instantiation. Up to 256 channels can be used per trigger port. There can also be multiple match units for you to match your signals against the same trigger port. So each ILA core supports up to 16 match units. So for example, if a user employed all 4 trigger ports and set 4 match units on each trigger port, that system would use all possible 16 match conditions. If you are building a more complex system, you can add additional ILA cores and cascade their outputs to check for complex trigger sequences that include up to 16 levels as shown in this diagram. In this case, you see multiple ILAs connected in series to allow for the maximum number of match units. Any design can contain up to 16 ILA cores. Since the ILA core is the most pertinent, it is supported with all 3 flows. While any design can have 15 ILA cores to make sufficient match units, note that the size and speed of the finished system can be affected. That is why we recommend that designers test part of the design each time and don't add as many cores to test the entire system at once. That is usually not necessary. The speed of operation of each core will vary by the chosen device family, speed grade, and options you set for each ILA core. It is important to verify the size of Chipscope cores before adding them to your design. To that end, be sure you leave the use SRL16s and RPM options asserted when customizing the ILA cores. This will save you LUTs and registers and reduce the size of your cores. The VI core enables you to insert virtual I/O pins into your design. It often helps to think of the inputs to the VI core as an output node from your design you wish to test, much like you would use an LED. Likewise, each output of the VI core is used as an input to a node in your design. For example, a user might force a value or pulse train into the FPGA by using a VI core configured as an output. Each VI core can be defined as an input or output and programmed to be synchronous or asynchronous to either the system clock or the JTAG clock. Each core can also support up to 256 bits. The Chipscope Pro software also gives you various ways to toggle the data. For example, you can use a pulse train or even text data to toggle the data. The VI core can only be added with the core generator flow. So keep in mind, you could still add the icon and ILA cores you need with the inserter flow. But you may find it easier to just use the code generator flow if you are going to be using the VI core for debugging. There are some things to know about the VI core. The VI core can only be created by the code generator tool. When the VI core is generated, it does not use the block RAM but uses the FPGA logic. The inputs are like LEDs for examining signals and the outputs are like switches or push buttons for driving signals. The core inserter flow, which as I mentioned, is also supported with the plan ahead flow and is often considered the easiest flow to follow because it is an automatic means of adding the codes to your design. This flow does have one significant limitation. It does not allow the user to sample nodes internal to an HDL component. Only post-synthesis nodes are available to be probed. So it is a good idea for you to maintain hierarchy during synthesis. After the user uses the core inserter to specify the post-synthesis nodes to be probed, the inserter will perform the translation phase of the implementation. This is necessary because in the code generator flow, the cores are inserted as a netlist. The flows were designed to be tightly integrated into the ISC tools and plan ahead. So this slide just summarizes the key points we have made about the core inserter flow. I'm not going to repeat what I have already told you. There are two new points here though. First of all, make sure all of your software is updated if you are going to use the core inserter or plan ahead flow. Especially since the plan ahead flow is new, you cannot mix and match software versions. Also, one minor point, keep in mind your implementation time will increase very slightly when using the icon and ILA cores. So in the first lab, you're going to add an ILA core to an existing design with the core inserter. As I mentioned earlier, this is probably the easiest way to add Chipscope cores to your design. This lab will give you a chance to use core inserter to add an ILA core. It also gives you an opportunity to customize an ILA core by setting trigger conditions and use the Chipscope software to configure a device, set trigger conditions, analyze, and debug a simple design. This lab shows Chipscope in its simplest form and shows how easy it is to set up, design, analyze, and debug your design. The file and lab instructions are in the zip file you can download with this slides and script. Note that the Spartan 6 SP605 demo board is used in the lab. But if you have finished pinout for your demo board, you should be able to use your demo board with this same design. All you will need to do is modify the design's user constraint file to match your demo board pinout. Now before we show you a little bit about the code generator flow in the lab, we want to introduce the plan head flow. As I mentioned, this is very similar to the inserter flow. It allows you to interactively select signals to probe from plan head software's netlist and schematic views. In this case, we see some screenshots that illustrate just that point. As you can see, we have synthesized the design and plan ahead has loaded the synthesized netlist and allows us to select some of the nodes from our design with the schematic viewer. This is a very easy and powerful way to set up for debugging, and many customers like this flow. We also see that our various trigger nodes are listed and can be managed with plan ahead. There is also a wizard that walks you through the setup of your Chipscope cores when using this flow, which makes it very user-friendly. The plan ahead software also inserts and compiles cores beside being tightly integrated with Chipscope. Selecting signals to be debugged is very simple with the plan ahead flow. As I mentioned, this can be done with a schematic view, but also can be accomplished with a netlist view. The netlist view allows you to see a list of input and output nets from each level of hierarchy and select which ones to add. The find command can also be used to find a particular node name you are looking for to complete testing. The size of each debug course can be easily found with the plan ahead flow, but also with the other flows. Since the cores are added as netlists, given the file extensions of ngC, they can be selected and their size determined easily. This is important because the amount of resources will vary by the number of match units you are sampling. Verifying the size of any component or netlist is normally done by right-clicking a component in plan ahead. This will automatically generate a GUI like you see here, where the number and type of each resource contained in the component is listed. However, plan ahead will also show you the connectivity of each core in a schematic. One of the other side benefits of plan ahead is the ability to make effective area constraints. Some customers choose to assign their Chipscope codes to specific area constraints in order to avoid routing congestion or to keep the core near critical logic. However, note that if you test nodes that are far away from the cores, then you can have some significant routing delay. With the code generator flow, the cores are instantiated directly into the HDL. This requires manually editing your HDL to make all of the necessary connections to the cores, and this takes more time to build. We will use this flow to debug the same design we used in Lab 1, but now we are going to use the code generator flow and also use the VIO core. If later on in the design flow you want to remove the cores from your design, you must comment them out. This process uses a standard implementation process that would be done by any designer wanting to add a component made by the Xilinx code generator. This is not merely an automatic flow, but does give you a complete control over the nodes you want to test, since you can probe inside of components. The code generator is now integrated in the latest 12.1 Plan Ahead tool. So you can now add these codes manually in the Plan Ahead design flow. In Lab 2, we are going to build on the knowledge we gained in the first lab. We will add an ILA and a VIO code to the design using the code generator flow this time. This lab will give you a chance to work with a different flow. Use the VIO and the VIO console cores to debug, control and monitor your design with the Chipscope software and be able to contrast the two flows, and it's a very worthwhile lab. The files and lab instructions are in the zip file you can download with these slides and script. Note that a Spartan 6 SP605 demo board is used in the lab. But if you have the finished pinout of your demo board, you should be able to use your demo board with this same design. All you will need to do is modify the design's user constraint file to match your demo board pinout. In summary, the Chipscope software enables you to shorten your debugging time by 50% and enables rapid debugging iterations. It also allows you to test your design component by component. Chipscope also enables you to test any node in your design and to test many nodes at once. You can add Chipscope cores at any time, either during design construction or after your design has been made. Each of the Chipscope cores has a specific purpose. The ILA core is used for viewing the operation of your device, and the VIO core is used for driving stimulus to your design and sampling data from your design. Adding the Chipscope cores make minor impact to the design. It usually enables you to test your design at system speed since the cores are optimized for both speed and to use minimal resources. You can learn more about Chipscope from Xilinx homepage. Just go to the CS Pro location specified here to learn more about what is offered. You can also view Chipscope recorded demos, access the 60-day license for Chipscope, and review the user guide and other software documentation. There are also recorded demos that discuss how to insert Chipscope cores and how to use Chipscope software to debug and verify your design. You can also learn more about Xilinx products. Xilinx FPGA Dynamic Probe combines the on-chip debug functionality with the power of a logic analyzer. The labs you are about to complete cover the most essential functionality of the Chipscope software. So be sure to spend some time working with the tools now that you have completed the training presentation. If you would like to learn more about other courses and RELs we offer, including our Chipscope Pro course, please go to the Education Services page. In this course, you will basically learn all that there is to know about each debugging flow. There are labs that go way beyond what we have covered, including discussions about trigger options, data visualization, scripting options, and a discussion about remote access. But whatever you do, please take a second and give us your feedback on this REL. All you have to do is click on the icon at the end of the recording and submit an evaluation. If you found this helpful, and I hope you did, it is important you take a couple of minutes and tell us that. And while you are at it, please let us know what other topics you would like to see covered in another REL. My name is Srikanth. Finally, thanks for listening to this recorded e-learning on the Chipscope Pro software. Thanks for your time and attention, and thanks for your business.